Welcome to the second part of Lecture 12 for Chemistry 418, the lecture on uranium chemistry and the fuel cycle. Part 2 of the lecture on uranium chemistry and the fuel cycle is going to focus on uranium oxide and uranium metal. There's a common point with these compounds. Both are used as nuclear fuel. For nuclear fuel, uranium metal shown here, and the oxide is dominant by UO2. It's UO2 2+. One thing that'll come out in the lecture when we discuss the chemistry of uranium oxides is that it's rather complex. Here we even see UO2, we see U3O8, we see UO3. In the lecture we're going to go into details on other uranium species, look at phase diagrams, understand that uranium can take multiple species as uranium oxides. However, one should understand from the lecture that the primary species are UO2, this U3O8, and we can even consider the trioxide, the UO3. In the nuclear fuel cycle, the uranium-oxygen system is of primary importance. This is due to the fact that one, the main fuel is UO2, and secondly, that the oxides are intermediate species in the formation of other chemical forms of uranium in the fuel cycle. So let's review some of the uranium oxide species that are present. Simple one, the uranium monoxide. It's very unstable. It has the sodium chloride structure, and you can form this by heating UO2 with metal. However, it's not a particularly stable system and tends to be a surface species. More dominant species is uranium dioxide. This can be formed by the reduction of a number of oxides, as shown here. Hydrogen can be used as a reduction. In our lab, we use 5% hydrogen and argon as a common route for producing UO2. These other compounds can also be used as reductants. Large-scale preparation is from a host of compounds that can be calcined in air. This would generally form either UO3 or U3O8, and then treated with hydrogen at a higher temperature. Under these cases, the resulting UO2 has a relatively high surface area. And here's the crystal structure of uranium dioxide. Another important uranium oxide species is U3O8, and this is formed from the oxidation of UO2 in air at 800 degrees. There's two phases, an alpha phase and a beta phase. That means it's U3O8 with different structures. And pictured here are some of the different structures. This is the alpha U3O8, should be U3O8, not U3U8 as shown here. And then this is the beta U3O8. And as you can see, for instance, here's a pentagon of oxygens around the uranium, and here's just a square plane of oxygens around the uranium. Here's that pentagon again, but you see that the relative formation of these pentagons changes. So this is just a change in the crystal structure. We often see this with compounds, and we'll really explore it when we talk about plutonium chemistry. Now, UO3, so uranium-6, can be prepared. There's 7 phases that can be prepared. There's not only listed with the Greek alpha, beta, gamma, but there's also an amorphous phase. If you heat in air at 400 degrees, so lower temperature, remember U3O8 can be made at 800 degrees, UO3 at this lower temperature. So we see that we can, if we take a uranium compound, UO3, produce it at 400 degrees. If we heat it at 800 degrees, we would turn this into U3O8. And here's a number of compounds that can be produced, oxalates, carbonates, that can be heated 400 degrees, makes the U3O8. We can change the crystallinity by changing the temperature. At certain times, this is often done in the laboratory. If we want to make compounds with different crystallinity, we'll often try to anneal them at a temperature so that the crystal structures form. And the reason that we're interested in getting compounds with crystals is then we can determine them by X-ray diffraction. The beta phase can be made by taking ammonia diuranate or uranyl nitrate and heating rapidly in air at between 400 and 500 degrees. The gamma phase has been prepared by heating the same sort of materials in air, under oxygen at higher atmospheres. Here's a complete route for making different uranium trioxides. You start with different starting materials, different temperatures, getting different phases. Now what we've just explored is the fact that the uranium-oxygen system is fairly complex. UO2, U3O8, UO3. In fact, if we look at the phase diagram of the system, we see as we change the oxygen to uranium ratio, here it's below 2 to about 2, a little bit above, we see that we have different species formed, including this one, UO2 minus X, so something that's sub-stoichiometric UO2. And then as we start getting higher in oxygen, we start forming some different species. Here's a U4O9 minus Y. Here's the higher ratio here. We see that we have U3O8 formed, UO3, U12O35, U8O19, U2O5. So there's a number of compounds we didn't necessarily explore, but the uranium-oxygen system is particularly rich, and as we compare it to the other actinides, we'll see that the other actinides do not have as many species. In fact, the uranium system is the one with the most species available. One of the things that comes out of this is that there's a way to tune the oxygen to uranium ratio. And as we see here, we have UO2 plus X or UO2 minus X. So for nuclear fuels, we can actually tune in the ratio of oxygen to uranium. And one of the ways of measuring that ratio is by looking at something like this thermodynamic data here, the Gibbs free energy as a function of the oxygen to uranium ratio. If one takes material and evaluates the enthalpy, not the Gibbs free energy, the enthalpy of the system, one can determine the oxygen to uranium ratio from this. Another important component in nuclear fuel is heat capacity. This is a thermal property, particularly with a material such as nuclear fuel, where you're generating heat and you want to transfer that heat to water or some coolant, and then make that coolant and that heat transfer turn a turbine. What we see here, there's a few different regimes where we have some different behaviors of heat capacity. From room temperature up to 1,000 degrees, we just see an increase in the heat capacity as a function of temperature. And this is due to lattice vibrations. So we're just heating up the entire UO2 lattice, and it's vibrating, changing the heat capacity. Above 1,000 degrees to about 1,500 degrees, right about here, we start to introduce anharmonic lattice vibrations. So this is a very simple lattice. This is anharmonic. So this is changing the system. We see a slight change in the behavior, the increase of heat capacity. And then above 1,500 K, we start to introduce defects, and we see a very, very large increase in heat capacity at high temperatures. This tells us something, one, about the behavior of the material at the high temperature, and two, how that lattice behaves, and gives us information about the strength of the lattice. For the nuclear fuel cycle, this is an important component where if we wanted to have a reactor at a given temperature, we can understand the heat capacity of the material, the fuel itself, as a function of temperature. Also, through the heating of this material, we can actually vaporize products out of the material. And here's an example of partial pressure of different products from UO2. So the oxygen dioxide, the oxygen itself, UO3, UO2, uranium, and UO, as a function of the oxygen to uranium ratio. And as again we see, as we hit 2.00, we see this inflection. We see a change of not only the total pressure, which is shown here. Total pressure jumps up above 2.0, but we also see a change of the species. And again, this is useful for determining the exact ratio of oxygen to uranium. And the reason that that's important, if you think about when uranium fissions, the fission products are going to want to form oxides. How much oxygen is available will dictate which fission products can form oxides. And as we'll learn when we evaluate the chemistry of fission products in spent fuel, we'll see that some metals, such as the metals from molybdenum up to palladium, form metallic inclusions. There's not enough oxygen around to oxidize those metals. So fuel can be tuned so that material will have properties of a certain oxygen to uranium ratio so that the fission product chemistry can be controlled. And the way one determines the oxygen to uranium ratio is through the enthalpy experiment that was done earlier or this vaporization experiment. So an overview of the chemical properties of uranium oxide is shown here. Strong acids tend to dissolve the uranium oxides. Valence tends not to change in these acids. They're non-oxidizing. Nitric, however, is an oxidizing acid. It will oxidize UO2 to U3O8. One can increase, if you have sintered UO2 pellets, you can increase the rate of dissolution with the addition of some reactants that will help drive the dissolution. For instance, peroxide will help oxidize uranium at the surface to the more soluble uranyl form. And here's an overview of some temperature reactions that some of you may be doing in the laboratory, where we have different starting products, oxides, and a reagent, and what can be formed from these reactions. For instance, there's a project going on where we're trying to look at the formation of uranium tetrachloride, and we're using other routes, but one could use, for instance, carbon tetrachloride at 400 degrees with UO2 to form uranium tetrachloride. And as we see, if we use U3O8, we get a mixed species, and the same with UO3. Another interesting property of uranium dioxide is its formation of solid solutions. And as a review, solid solutions basically compounds that are formed from a mixture of species where the crystal structure is unchanged by the addition of one compound to another. In this case, this mixture, what we call the solid solution, remains as a single phase. And as an example of a solid solution is thorium dioxide and uranium dioxide. Here's the crystal structure of UO2. The uranium metal centers are shown here. In a solid solution, thorium would just replace one of these uranium metal centers. The lattice may change, the distance between the thorium and the oxygen and the thorium and the next thorium may change, but the crystal structure remains the same. That's our solid solution. And what's interesting property about that with uranium dioxide, it means that in nuclear fuel, compounds that form solid solutions can remain in the nuclear fuel and have the same crystal structure. So solid solutions are formed with UO2 with group 2 elements, lanthanides, actinides, and some transition elements. Now the degree that they form these solid solutions varies. For instance, the lanthanides can quickly, if you put enough lanthanide into the uranium dioxide, you'll form separate phases. So the degree of a solid solution is based upon how similar that crystal structure really is to UO2. That's why thorium and uranium dioxides, the ionic radii are similar, the structures are similar. They form very good solid solutions. These solid solutions can be prepared by heating oxide mixtures under reducing conditions because you don't want to oxidize the uranium, between 1,000 and 2,000 degrees. And they're often written as something like this, where you have one metal, uranium, and oxygen. So this could be thorium, uranium, oxygen. X can be positive or negative, or in the case of thorium, uranium, X would be 0. Now this synthesis condition is similar to what occurs as uranium dioxide fuel is burned in a reactor. So as we saw in the previous slide, we discussed that if we start adding components to UO2, the structure doesn't change, but the lattice parameters might. And here's an example of the lattice parameters of uranium thorium dioxide. And as we see here, there's with this wet milled condition, a very linear relationship. This is called Veygart's law between uranium dioxide and thorium dioxide. So this is weight percent thorium dioxide. So here's 100 weight percent uranium, 100 weight percent thorium. And we would just see that the lattice parameter, this is the lattice parameter for thorium dioxide, this is the lattice parameter in angstroms for uranium dioxide. A mixture is just a linear combination of the two. So something that's 50% would be the lattice parameter would be a contribution of 50% of the uranium dioxide and 50% of the thorium dioxide. This is a way if one takes a compound as a solid solution and measures the lattice parameter with X-ray diffraction, you can determine the composition of both. So this linear change is Veygart's law. And here's an example of compounds that make solid solutions with UO2. Zirconium, for instance, makes a solid solution up to a certain level of zirconium, after which, when more zirconium is added, it forms a separate phase. This is due to the fact that the zirconium is a much smaller ionic radius, so when you start adding enough in, it no longer fits comfortably into the uranium dioxide lattice and forms its own. So if I were to take a compound and exceed where Y is 0.35, so make something where in an atomic ratio where it's 35% by atom uranium. If we went to conditions where we added more uranium so that this value was larger, we'd get two phases forming, one that would be the separate phase of the compounds and one that would be this solid solution. Unlike the zirconium, thorium, which has an ionic radius very similar to uranium, they're both about 1 angstrom, where zirconium is about 0.72 angstrom, so it's much smaller. Thorium makes a solid solution with uranium over the entire range. Some tri- and tetravalent solid solutions, well, cerium-4 is continuous over the entire range, whereas cerium-3 has variations. And the tri- and divalent solid solutions really depends upon whether you're in a reducing or an oxidizing environment. One of the take-homes for this is when we look at the chemistry of the fission products in UO2, whether or not it'll form a solid solution with uranium, those fission products will be based upon the amount of that material and the relative crystal structure compared to the UO2. An example of the uranium-zirconium oxide system is shown here. This is the phase diagram showing temperature plotted against the percent by mole of UO2. 100% UO2, 0% UO2. So you would imagine a nuclear fuel. You would be somewhere in this regime. We'd have solid solutions in areas that are marked by the purple. So over here we'd have face-centered cubic structure dominating in this area. When we got to higher and higher amounts of zirconium, obviously more than you would see in nuclear fuel, you would have this face-centered tetragonal form dominating. You'd have a mixed phased here and then a monoclinic form here. Within this regime, at lower temperatures, we have two species formed. Now, this regime shown here, we have multiple phases formed, face-centered cubic and face-centered tetragonal. So when we started to reach percentages of uranium that were lower than what's shown on that side of this solid solution regime, we start having mixed species. Now this is an example of a system that's important for nuclear fuel, as zirconium is a large fission product. It's also been explored for inert matrix fuels, but this system is also rather complicated, and you can find different data in the literature. The solid solution behavior of the UO2 species is similar in respects to the pure species when it comes to the oxygen to metal ratio. Again, if one is making fuel out of solid solutions, one may want to control the relative amount of oxygen in the system, and one could do that similar to what was done with the uranium dioxide by looking at a thermodynamic parameter, in this case the Gibbs free energy, as a function of uranium or oxygen to metal ratio. For the zirconium solid solution, data has been collected. For the thorium solid solution, there's an increase in Gibbs free energy with increasing Y, the amount of thorium. Compared to the UO2, difference is small at Y less than 0.1. And then here's an example of the data for the gadolinium system. As we see, as a function of Y and temperature, you can determine the ratio of oxygen to gadolinium plus uranium through the Gibbs free energy. Cerium has also been studied. The shape of this curve is similar to the plutonium system, but the value is different. So what this means is that there's data available to determine for uranium-containing solid solutions the ratio of oxygen to the metals. And this is done through evaluation of thermodynamic data, and in this case, the Gibbs free energy. Metallic uranium is also a potential nuclear fuel. And as we'll see with some of the other actinides, the metal phases of the actinides can be very complex. Uranium has three phases: alpha, beta, gamma. They dominate at different temperatures. Uranium metal itself is strongly electropositive. That means that we cannot be paired through reduction by hydrogen. As we already discussed, if I want to make uranium dioxide, I can take higher oxides, treat them with hydrogen and under heated conditions, and make UO2, so that's uranium-4, but the hydrogen will not drive uranium down to the metal. So that means to prepare uranium metal, I have to use a different route, and what's done is shown something here, where we make fluorides of uranium. We take those fluorides, treat it with magnesium metal, so a divalent metal or even a monovalent metal would be sufficient to reduce uranium from the +4 to the metal state. So this preparation can be done with uranium tetrafluoride or tetrachloride with calcium or magnesium. You can also use UO2 with calcium, or you can do electrodeposition from molten salt baths. And as we talk about uranium processing or nuclear fuel processing, one of the methods is electrochemistry, in which the material, the nuclear fuels, is dissolved in molten salts, and then electrochemistry is performed in these molten salts. Molten salts will not form the same reactants as water, so we can take potentials and drive the metals down to their metallic states in a molten salt and not react the molten salt. And if the molten salt is made out of sodium or lithium chlorides, what we're saying is that the potential for the formation of the metal is less than or is greater than the potential for the formation of the metal from the salt. So in other words, it's easier to make uranium metal than sodium metal or lithium metal, depending upon what's in the salt. This is also a reason why ionic liquids are examined as potential routes for treating nuclear fuel or treating uranium, because they have the same large electrochemical window and will allow the formation of actinide metals in those solutions. So here are the different phases of uranium metal, where we have the alpha phase. It's good from room temperature. It's formed from room temperature up to about 600 degrees. The structure is orthorhombic, and the uranium distances are around 2.8 angstroms. This is what the structure looks like. The beta phase exists in a relatively narrow temperature range. Tetragonal unit cell, shown here. And the gamma phase is formed above 775 degrees, and that has a BCC, body-centered cubic structure. The metal has different characters. It can be some plastic character. The gamma phase is soft, difficult for fabrication. The beta phase can be brittle and hard. These materials can often be alloyed. The uranium materials can be alloyed so that compounds can be formed that are easier to fabricate, for instance, or that have certain chemical resistivity properties. And uranium alloys well with molybdenum, niobium, zirconium, and titanium. Similar to the solid solutions, the metals can also form different compounds. The alloys, as we've already talked about, those are just where the metals form fundamentally solid solutions, but the metal ions are just replacing each other. Intermetallic compounds can also form, and these are compounds that have specific stoichiometries. So for instance, uranium with manganese, iron, cobalt, nickel, that composition in stainless steel, can form a U6X compound. So that intermetallic has specific stoichiometries, and these compounds will form. So if you had uranium metal against stainless steel, which can occur in a fast reactor, and you started to have diffusion of the stainless steel into the uranium, you would change that uranium metal to this intermetallic compound. Noble metals can also form compounds with these intermetallic compounds with uranium. And then as we discussed with the alloys, we get something that looks more like solid solutions. And here's a table that says what's the form, what metals form those compounds. So intermetallics are formed with all these metals. Solid solutions tend to be formed with these metals. And phases that separate tend to be formed with these metals. So for instance, in metallic fuel, the lanthanides, shown here, as they're being produced, will phase separate and form different phases in uranium metal. Here are an example of two phase diagrams. We see uranium and the aluminum phase diagram. This is the liquidus phase. Here's uranium, here's aluminum, here's 100% uranium, and these are the different phases. So we'll get, if we start having mixtures, we'll form two phases here, one being the uranium metal and one being this intermetallic uranium aluminum 2. If we had a compound, if we mixed uranium with by weight with 25% aluminum, it would fall right about here, and we would have a mixture of compounds based upon where it falls on this phase diagram. Over here, the 25 would be primarily the uranium-3 aluminum with a little bit of the uranium-2 aluminum. And titanium, we can form some of the alloyed species along with some intermetallic species. So again, depending upon the exact amount of material, generally alloys are better if you have a relatively low amount of material in the uranium metal. Even titanium, we said that it alloys, but at a high enough concentration, we start to form these intermetallic species. The chemical properties of uranium metal and its alloys are listed here. Uranium metal reacts with, you can form alloys or intermetallics with a lot of the elements on the periodic table. The metal itself can be corroded by air, water, even under elevated temperature with carbon monoxide. This often means that if you store uranium metal, you store it under oil, so it prevents air interactions. The metal dissolves in HCl, and non-oxidizing acids can result in slow dissolution. The metal, especially if it's powdered, large surface area, forms lots of heat when it is dissolved in nitric acid. And it can dissolve in a base with the addition of peroxides. And it forms these peroxyuranates, which are unique compounds amongst the actinides, where peroxide species can be formed, and we've already talked about that in separations, where peroxides of uranium is one of the routes of doing a selective precipitation of the material. And here's a review of reactions of uranium metal. Again, imagine doing this in a tube furnace. We have different reactants, different temperatures, and different products. As we talked about earlier, if we were interested in forming uranium chlorides, we can react uranium metal with chlorine gas. You get a mixture of chlorides at 500 degrees. Or if we took uranium metal and reacted it with HCl, we can get the uranium trichloride at 300 degrees. Within the lectures on uranium chemistry, we really focused on how this chemistry of uranium is linked with the fuel cycle. There's some fundamentals in the solution phase, primarily the fact that the uranyl species, the UO22+, dominates, that UO2 has linear oxygens, and those are formed due to the role of F electrons in this compound. So that uranyl, we're also going to see that other actinides have these eel species, these linear oxygens. Neptunium, plutonium, americium also shows this, and they're dominated by +6, as we demonstrated with uranium, but they'll also be evident in +5 oxidation states, such as with neptunium. So this linked chemistry with the fuel cycle also extends to other areas of the actinides. We've discussed different oxidation states of uranium, primarily the 4 and the 6. However, you can make compounds of the 3. The 5 is difficult to make, but can also be made. And this multiple oxidation state chemistry is also going to be indicative of the transuranic actinides up to plutonium. Americium does have multiple oxidation states. Curium has one other oxidation state. But it's a rich number of oxidation states for uranium, neptunium, and plutonium. And again, these are driven by the behavior of the F electrons. So that's some information that you should have gotten out of this lecture. That'll be extended to other lectures on the actinides. You should be able to describe enrichment processes, mass-based and laser-based. In terms of describing the enrichment processes, one should understand the fundamental chemistry and physics that drive the enrichment process, not so much how those processes are linked together in cascades and how the engineering systems are utilized to achieve the enrichment levels that are necessary for nuclear fuel. You should also understand some of the fundamental chemistry of uranium as it relates to the production of uranium from ore, so that's again separations, solution chemistry dominated by the uranyl species. Important ligands in the environment could be hydroxides and carbonates. Speciation of uranium, a key component in solution chemistry production in terms of separations. And uranium spectroscopy. There's UV visible spectroscopy and laser-based fluorescence spectroscopy. Some questions that you should be able to answer based upon the two lectures are listed here. One would be, what are the different types of conditions used for separation of uranium from ore? Well, there's two types of conditions. One would be an acid leaching, for instance, with 1.5 molar sulfuric acid. Uranium-6 is soluble in sulfuric acid forming anionic species, so uranyl sulfate. Anionic species are also formed with carbonate leaching. So in a basic system, you can form carbonate systems. The uranyl carbonate will go into the solution phase. And this is beneficial because a lot of metal ions will then go into the solid phase, so you can achieve an initial bulk separation with this route. So what's the physical basis for enriching uranium by gas and laser methods? And that's a cascade. In other words, that you have an enriched phase, which is then used as a feed for further enrichment. So it's not a single step, but many, many stages that's needed to do enrichment. What are some of the basic ways of producing uranium metal? Well, we want to be able to reduce a uranium cation to a metallic phase. So for instance, halides of uranium can react with calcium or other group 2 elements, where we form, for instance, the group 2 halide or fluoride along with uranium metal. The oxide can also react with calcium, forming calcium oxide and uranium metal, or electrodeposition from molten salt baths. Even ionic liquids can be used. What are some of the natural isotopes of uranium? As we discussed earlier, there are the uranium-235, which is 0.7%, uranium-238, which is the bulk of the uranium, and then some uranium-234, which is in equilibrium with uranium-238 due to the decay route. And some synthesis and properties of the uranium halides. Well, we discussed those previously, where we talked about starting compounds for the formation of uranium metal, and these can be achieved either from using the uranium metal with the acids or the gases. We discussed in this lecture that the uranium to oxide ratio can be tuned for nuclear fuel. How was this ratio determined? One way is to look at thermodynamic data, and shown here is the example of the enthalpy as a function of the oxygen to uranium ratio, and we see some broad changes. We see a spike at around 2. Then as the ratio slowly increases, we see some systematic changes within the system. So if one measured the delta H for the system, one can determine the oxygen to uranium ratio. What are some trends in the solution chemistry? Well, particularly if you look at oxidation state, we see some trends, for instance, with complexation with water, formation of hydroxide or precipitation, that the tetravalent is the one that will precipitate the most. The trivalent and hexavalent species are similar, and the pentavalent phase, which is not readily formed, is the least likely to form a hydroxide species. So the hydrolysis constants can dictate that trend. What are the atomic orbitals that are used to form molecular orbitals for UO2? Those are shown here. These are just the F electrons orbitals that have overlapping with the PZ, the oxygen P orbitals, and the oxygen S orbitals. What else can be used instead of U-235 as a fissile isotope in a reactor? Well, the other uranium isotope one could use would be uranium-233. And describe two processes for enriching uranium: a laser-based method, two gas methods, centrifuge and diffusion. And why does uranium need to be enriched? The amount of natural uranium-235 is 0.7%, and for light water reactors, you would like that fuel to be above, let's say, around 3%. So that 235 needs to be at a higher level, and that's called enrichment.
When you have completed the lecture, please comment on the blog and respond to the lecture quiz. From this lecture, one should understand the different chemical forms of uranium, primarily that the uranium solution species is uranyl, the hexavalent oxidation state, that is UO22+. You should understand that uranium compounds can have oxidation state ranges from +3 to +6. You should understand that oxides of uranium can have different stoichiometries between uranium and oxygen. We will discuss more about UO2 as it is the primary uranium form in nuclear fuel. But within this lecture, we discussed a range of different oxides and how they relate to the uranium oxidation state and the synthesis properties of these oxide compounds. The lecture also reviewed uranium metal properties. You should be familiar with the metal properties of uranium, the types of compounds that can be made, intermetallic, solid solutions, and understand how to utilize phase diagram information to determine some properties of uranium metal compounds. You should comprehend and describe the role of 5F electrons in uranium bonding with uranyl as an example. The molecular orbital diagram that was presented in the lecture should be a primary source. You should understand and discuss methods that are used for uranium separation. There is an additional lecture on separation, which we'll go over this in more detail. But within this lecture, we discuss some initial routes for uranium separation. And finally, the lecture discussed uranium enrichment. From this, you should be able to describe, understand, and comprehend why and how uranium isotopic enrichment is performed.